Hello, Physics 30s. I wanted to just clarify what a DC motor does. Sorry for my birds here. Um, and help you understand a little bit of the third hand rule. So this here is a DC motor, and you can see that there's some components working to it, but really a DC motor is made up of a bunch of separate loops like this. So you can see that this loop is connected to a power source, and it shows the magnetic field from north to south, the yellow arrows. And the part that moves is called the armature. And the armature is hooked up to a split ring commutator that's highlighted in blue right there. And that's hooked up to some brushes, which is hooked up to a power source. So uh, what we do is we run electricity through the loop, and then the loop starts acting like a wire because it generates its own magnetic field. The only problem with this animation I'm showing you is the blue arrows are in the wrong direction. The current should flow from the negative terminal to the positive terminal, so the blue arrow should be flipped, but otherwise it's right. Okay, they're using kind of an old conventional current method here. But I like the red arrows. The red arrows show the force on the loop of wire. So you can see near the south pole, your left hand, your fingers would point from north to south, and your thumb should point in the opposite direction of the blue arrow at that point. But then your palm pushes up near the south pole. So that red arrow up shows the force on the loop there. And then if you go to the other side near the north pole, you could do the same thing, and your palm would push down. Um, Thing to note about any loop like this, the only parts of the loop that are affected by the magnetic field are the parts of the loop that are perpendicular to the magnetic field. So you'll see, like, as you come around the loop on the top part, there's no red arrow there because that part is parallel with the magnetic field. Okay, and you'll see that kind of as the animation continues. So I'll just let it play for a little bit. There's a really clever trick that we do. So I'm right at the beginning here. I'm pausing this, but at the beginning, the loop will get pushed because of the third hand rule. It'll get pushed up near the South Pole and down near the North Pole, but that'll only happen to a certain point because eventually, see, the force will just keep pushing upwards and the loop will stop turning. But you'll notice here in the animation, it highlights this light blue and dark blue split, because now what happens every half turn is, now if you can follow it, the bottom part of the loop now is going to have the current going through that way. So the current is going to change direction every half turn. And I know those arrows are wrong, but the red arrows are right. So the red arrows, you can see every half turn, the current changes direction, and so then the force changes direction. So if you let your eye follow one part of the loop, then the arrow is pushing up on it as it comes to the top, and then the arrow pushes down on it. So it's a very clever adaptation. Michael Faraday gets a lot of credit for figuring this out, and in this manner you can keep the loop turning. Now, as the animation shows, though, in a real DC motor, if you just had one loop, it would not run very well. In fact, it would kind of stutter. It would kind of go for a little bit and then lag, and then it would pick up, just like it's showing you right now. And that's not a great motor. So any DC motor you come across isn't going to have just one loop. It's going to have lots of loops. And the more loops you add with their own, connecting section on this commutator ring, as you see how this adds, the more loops you have, the better, because as one loop is lagging, the next loop can start getting pushed. And so, yeah, most DC motors have like 8 or 12 or some symmetrical number of loops that will enable a DC motor to turn. So two things I want you to take away from this is the only parts of a loop of wire in a magnetic field that will get pushed are the parts that are perpendicular to the magnetic field. It gets kind of complicated if it's a circle. I'm not going to do that for you. We usually do like a square loop or something. And so only the lengths of wire that are perpendicular to the magnetic field are the lengths that are going to experience the force. Any lengths of the wire that are parallel to the magnetic field are not going to get pushed. So you would ignore those in your calculation in terms of determining L, the length of wire that's actually in the magnetic field. Obviously, the more lengths of wire you have, and that's how you can make a motor go faster, just put more and more loops in there, and then the force will go up because the force magnetic is proportional to the current flow and the length of wire and the strength of the magnetic field. I hope that was helpful.